Okay, so it's 11:30, so with no further ado, I'd like to start off this next paper session. And we will be starting with Ben
Oops.
Weatherfeld, who's presenting the minimum cut pitch spelling algorithm. So welcome, Ben.
Thank you. Thank you very much. I am speaking to you from Los Angeles, and it is 2:30 a.m. here, so you'll have to excuse me
I'm
if I'm a
so
little bit
I
out of it.
I'm so sorry. I had no idea that you were in Los Angeles. I would have scheduled you for a different time. But thank you for showing
No
up.
problem. Yeah, for the cause. Yeah. So anyway, yeah, so just a little bit of background. I was working on pitch spelling and doing it algorithmically during my undergrad at Harvard. And I'm currently, unfortunately, I can't devote as much time to this as when I wrote the conference paper way back in 2019, because this was from the first rescheduled conference. I'm now over in Cambridge working with liquid crystals and things, but it's very nice to be here and be able to present this work. And my dream scenario is that someone is sort of curious enough that they might want to take it on or talk about it, or who knows. So anyway, so this is just to kind of give a quick demonstration, I guess, of sorts of my credentials. I guess I used to do the composition thing in my teenage years and into my early adulthood. And so I guess, I'm sure a lot of people have that background, but what I learned is that notation is important. And I think, I heard this talked about in at least one other talk, just, when you're in the business of notation, it's one part of a long chain of kind of a lossy chain of getting your musical ideas to listeners. And so, with something like pitch spelling, we're focusing on refining notation so that there's fewer ambiguities, basically, and you can get your rehearsal process as smooth as possible and so on. So there's an illustrious history of work in this field. I'm most certainly not the first person to try to come up with a pitch spelling algorithm. Chen and Chu had a nice diagram from their paper. And I guess I have some music here. I wonder if it'll play. I'm sure a lot of people will recognize this piece, but anyway, that's just a bit of light relief, I guess. So that's where the page starts, and basically we've got the arrowheads are. Let me see if I can stop this from playing. Actually, oh no, I can't. Yeah, so the arrowheads are where the performance of the Chen and Chu algorithm, and then the red circled note heads were mistakes made. Mistakes made by the Chen and Chu, and then the circled red blobs were mistakes made by commercial notation software at the time. So it would have been Finale and Sibelius. I forget which way around they are. But I haven't tested particularly recently, but I think there are still problems. This is only Beethoven, but especially if you're getting into situations where you're putting down collections of pitches where there isn't really one right answer. I think sometimes the defaults, at least in my experience of the notational software, the commercial programs are leave a little to be desired. So just recapping what I was saying, this is just Beethoven, but clearly the problem is quite tricky. And, when you have a harmonically complex passage, you've got various problems that are leading to ambiguities in spelling. And I've called them here degeneracy, having many options per pitch, and relationships being basically that your pitch spellings are determined by intervallic relationships. So it's very kind of context dependent, and it's difficult to kind of nail it down. This is another one where I could, will this play? Should be a video, but maybe not. Oh, sorry. So anyway, this was just an example of, it's a collaborator of mine. I think there are like a ton of examples from the conference as well, of a kind of dynamic notation software, where this kind of being able to spell pitches on the fly would be useful. But I can imagine, I'm sure the designers already think about this kind of problem in things like max score or even OM sharp that we just heard about in the previous session, and so on. So anyway, this is just basically for a non-musical audience, because I've given a version of this talk before. This is just showing all the enharmonics and how there's just a big minefield of possible spellings. And essentially you want to preserve good intervals. So this is an example with an augmented sixth chord. It's a little bit contrived, but basically it's showing that on the left you'll have a certain, even though it's not always just about having flats near flats and sharps near sharps. Like if you've got an augmented sixth chord, obviously it's more about various voice leading concerns as well. And then on the right hand side, all those nice intervals have gone away, and it's very difficult to see what's going on. So again, these are the two problems that go into it. So I just wanted to, in this talk, basically give a quick overview of how I approached modeling this problem, and yeah, just to give a flavor. And then there's a little bit more in the paper, the accompanying paper, if people are interested beyond that. So yeah, so we've got this problem of relationships between pitches, and so essentially you can think of that as almost like a network structure. So where the nodes are representing what will become note heads in your score, but are basically pitches. And then we need basically, and for reasons that will become clear, we need some kind of encoding system for describing the various enharmonic options we have for each pitch. So I've done this basically with two binary variables, so they can be 0 and 1. If they're both in the 0 state, then your flattest spelling. So for a lot of pitches, so for pitch class 0, that will be D double flat. For pitch class 1, that will be D flat, and so on. That's on the left, it's a little small. Sharpest spelling, on the other hand, is 2 1s, and then your natural spelling is 0 1. So for a lot of, for any white notes on the keyboard, the natural spelling is just with the natural accidental, which makes sense. And then for some, it's somewhat arbitrary. You kind of have to choose between whichever one is left over. So in the case of something like E flat, maybe a toss up between E flat and D sharp, but D sharp was already the sharpest spelling. So that's how the encoding system works. And then essentially the idea here is we keep our network structure, but we just, we superimpose 2 nodes in wherever there was 1 node. And we add these S and T, source and sink nodes. And basically we're embedding, when for each pair of nodes that was previously represented by 1 node, we have one of these binary variables, and that's how we're representing our pitch classes and their spellings. So here I'm just showing we've got the lower pitch on the right-hand side is pitch class 3, and it's in its natural spelling form, which takes it to E flat. And pitch class 1 is in its flattest form, which takes it to D flat, which is a nice collection of, or dyad in terms of the spelling. So what I've been hiding from you is that we're recasting this as a famous type of problem in optimization and linear optimization, which is called the minimum cut problem for flow networks. And essentially you're looking for the, you have a weighted graph, directed graph. So essentially you've got these numbers attached to edges, which represent some kind of weight. And then you're finding the collection of edges that separates S from T that has the lowest total weight. So here we've chosen the 3 1s here, and the total cut is a total weight of 3. And that's, you can check, that's the least that you could get for this graph. And so what's the reason for the reason that this is helpful is that essentially everything on the S side becomes a 0 node, and everything on the T side becomes a 1 node. So that kind of maps back onto what we were trying to do in terms of assigning 0s and 1s to our nodes, so that by solving for this minimum cut, we've essentially spelled our collection of pitches. So that was kind of an interesting application of this well-studied algorithm and problem statement from optimization theory, which was applied to the pitch spelling problem. So we're left with the problem of kind of where we derive our edge weights, and so essentially you want to find edge weights that will give you the right cut. And so there have been a couple of approaches I've looked at for this, still a little bit in progress. One is to do some direct inverse algorithms on the flow networks, which is something that's described in the paper. And then the other plan would be to do almost like a big learning project using large corpora of musical scores. So yeah, like I said, this is what you'll find in the paper. And then I'm working on the kind of big, multi-score approach. That's stalled a little bit because I unfortunately have to work on my PhD. But in the unlikely event that someone's been intrigued by this or wants to get involved, I'd be so delighted. And so, so next steps are essentially doing this big kind of machine learning type task, then validating against large sets of scores. And wouldn't it be nice to implement it in real notation software eventually? So yeah, this is just kind of saying what I talked about today, and here's the paper, and thanks.
Great, thank you. That was super interesting. Let's see. I think there's a question here in the chat. In the slide of relationality about good and bad spelling, and the later slide, why is the +1 sharp as 3/4 sharp microtonal? I noticed that too. There was there's a funny sharp sign there, which is I don't know if it was
probably a typo.
Provocative.
Well,
microtonal.
Oh my goodness! You're
because
so right.
That opens up a whole other problem, of course, when you're dealing with microtones and
well,
this sort of
actually,
thing.
It's funny that I made that slip, because one of the initial motivations of this model was to basically make an approach to pitch spelling that would extend to microtones, especially like, you know, just I guess, what do they call it? 48 EDO. So essentially where you've got like equal temperament, but up to 48 steps. So where you've got quarter and eighth tones. Yeah, that's one nice thing about this method, which I hadn't seen in other approaches to pitch spelling. So the idea, at least, is that it's supposed to be kind of agnostic to things like, well, as agnostic as you can be to kind of scales and so on, is more based on intervals, so that it's good for new music. But again, I'm still in the process of sort of testing that on a large scale.
Yeah,
there's another hand raised.
Super. Oh, is there? Let me go to the other view.
It's me.
Okay, please.
Georg. Thank you for this really interesting, inspiring presentation, Ben. Of course, we shouldn't forget that enharmonic spelling, or accidentals in general, are representing harmonic relationships. Mm-hmm. And that's what I really like about the extended Helmholtz-Ellis just intonation notation, mm-hmm. because it's a fantastic system to capture harmonic relationships. Have you also considered encapsulating that in your approach, like something like some sort of a harmonic analysis?
I think that's a really good point. The way I was conceiving of this, at least initially, was that if you are using some kind of music notation program, this could present you with like a good default, let's say, like kind of pretty good starting point for your spellings, and then you could change the spellings to suit if you had a very intentional intervallic relationship that you wanted to accentuate with the, I forget what they're called, the Ellis notation as well. I mean, that stuff's super interesting. I think one thing about if I'm not mistaken, one thing about relationships with those accidentals is that I don't know if do you have the same amount of kind of redundancy? Because it is so expressive, I was wondering if kind of it says how far around the kind of cycle of Pythagorean fifths or whatever it is that you've gone.
Yeah, it's a good point. I'm not sure that it's there's the same enharmonicity as like when you're talking about just intervals. You can't. I think that's partly the point of this just intonation notation, is that it's a very specific. It can only be represented. Actually, wait, that's.
It also has an extension which enables you to represent tempered intervals. You have that little line over the flats and sharps and naturals. But of course, the intention of the Helmholtz-Ellis notation is to take out redundancy and particularly ambiguity. So you are, of course, the way the enharmonic spelling offers a fair amount of ambiguity the way we're handling it, and also enables us to do modulations and harmonic modulations, so the way composers used to do this throughout the 18th and 19th centuries. But I think it's still would be still interesting to use machine learning to the extent that you have a system that's capable of realizing these harmonic relationships, and also then make an informed decision on how to spell or respell these accidentals, particularly in pivot chords, because pivot chords pose a particular challenge, because you really have to decide how to spell the chord. If you don't repeat it and repeat the kind of the pivoted version of it, if it's just one statement, then you have to decide whether you want to use the you know, the spelling from the original context or the spelling from the target context. So that's very interesting, and of course machine learning will help a lot in this context.
Definitely, yeah, all really interesting, far-sighted points, I would say. Thank you very much.
I guess we should move on to the next paper. I'm just curious, though. There must be some relationship to fluid crystals that could find a relationship to. No.
If anyone knows of one, please let me know. I'd be very interested.
Well, it sounds like a fascinating second research that you're doing, and I hope that will continue, that you'll still be able to keep on with your musical work as well.
Well, thanks very much for having me.
Yes, thank you for joining us. Okay, so our next speaker is Elona Shatri, who is presenting a paper with György, Fazekas?
Yeah.
Thank you. On optical music recognition, state of the art and major challenges. And so I will.
Can you see?
Yes.
The slide full screen?
Yes, looks great.
Okay. Hi everyone. So I'm Elona Shatri, and I will be presenting today alone. György Fazekas is my supervisor, and we work together in optical music recognition. Today I will present the paper from last year, which is a review paper on the state of the art and the major challenges in WebAR. Today's agenda is this, so I don't step too much on this one. So I will start talking about music representations. That is essential for a good OMR system. Okay, just a second. Got the problem. Is it okay? Yeah. The primary purpose of early music representations was to record the music for the purpose of reproduction of the music by performance. With music becoming part of academia studies, music notations became more than just performance instructions by also providing data for research and teaching. At the end of the 19th century, there was some technology involved, which at that point meant recording the audio of music audio. But the data representation, it lacks structural information, which a music score, a written music score, would be able to show. But in the other side, it did give a very detailed musical signal. In the late 80s and the early 90s, there were several attempts to produce symbolic representations of music, and there was also some research in the philosophy and the mathematics underlying this representation. However, no consensus was achieved on the appropriate features for music representations. In the early 2000s, more systems came to light. These representation models did actually capture a lot of music features such as stuff notations, but also missed a lot of it as well, some more difficult features. There were some attempts to represent music in ways which conform to the principles of what we call knowledge representations. And in fact, that was developed by the artificial intelligence community. Their specifications include inference systems, temporal logic for music, and a general ontology for the presentation of music. Computer encoding of data is meaningless without a method to interpret it, and that is, and if that method is buried in the implementation of a program, it is formally opaque and is very prone to errors and generally inaccessible, which are the features we don't want in a good music representation system. The primary purpose of computer systems is to manipulate it, as we know. However, data can be presented in different ways. Even the same data can be presented in different ways. This raises the problem of non-interoperability encodings. Data abstraction tries to avoid this problem, identifying and making explicit properties of the data which are specifically relevant to a particular task or situation to be addressed by a program. Information begins in a paper published in 2014, if I remember right. He mentions several points or characteristics of a good music representation system. I will present some of them, not all of them. We'll present what we think is relevant to OMR. We mentioned already data abstraction, and then I'll continue with information content, which includes expressive completeness, which is the extent to which the original content of the music represented may be retrieved or created from the represented knowledge, and then structural generality, which is the extent to which information about musical structure may be restored in the representation. It's interesting because these dimensions are orthogonal to each other. And at the same time, they're both equally important to OMR. So finding a good balance between the two is highly important for the OMR field. Some researchers say that, it's well known that musical knowledge is multiple hierarchical in the sense that many different hierarchies can be constructed at the same time and on any given musical surface, which is an attribute of music that poses actually the main challenges to OMR. However, there may be annotations on these hierarchical structures which are not part of the constituent hierarchy. These annotations describe relationships between parts of the hierarchies, which are based not purely on a structural inclusion, but rather on a more subtle musical relationship, such as similarity. There is also a need for a formal description language with appropriate primitives and combination operators for describing relationships within and between musical elements. I will now explain what OMR is. The music notation is much more precise and complicated than written language. When we notate music, we use symbols to represent all the musical features needed to reproduce that piece, as mentioned earlier. Being able to retrieve such information from sheet music and read it computationally is the core of the OMR, or optical music recognition problem. OMR has been previously also called optical character recognition for music. However, music scores carry much more information in a more complex structure with ordered sequence of music symbols together with their spatial relationships. In contrast, OCR deals with sequences of characters and words that are one-dimensional. Inputs to the OMR systems are images of scores. As for output, there's a diversity. For instance, if in the left side we see a piano roll, which can be, which is an output that is can only be played, but the exact symbols cannot be retrieved. So we don't have a graphical sheet music from that. In the right side, we can see an output, a rendered version of the score that encodes all the music elements. And all these outputs actually depend on the domain we choose. Is it acoustic, auditory, or graphical? Considering that the biggest challenge in OMR and other MIR tasks, music information retrieval tasks, is the lack of a good representation system, work in OMR has been limited to these challenges. That affects the type of music OMR can work with. And that is mainly limited to monophonic scores, which most of the current work works on. Why do we think OMR is important? There is a substantial number of music tools and software that allow things like creating demos, editing, rendering, choosing engraving styles, and many more possibilities. Digital musicology studies musical forms across tradition, genre, culture, time periods, and composers, leaving machine-readable files. Having machine-readable files in this case would highly assist in the field. Optical music recognition also enables searchability, computational analysis, assessing the way music information retrieval works. Furthermore, it would allow conversion to different sheet music formats such as Braille, so actually increasing the inclusion. OMR is conventionally tackled in 4 stages: image processing, object detection, object reconstruction, and finally encoding. In the first stage, images of music, sheet music, are subject to reprocessing methods such as enhancement, binarization, deskewing, blurring, in order to make the rest of OMR process more robust. Then the stage of object detection comes in, where there is classification of the primitives, detected objects. And then all these detected objects need to be retrieved and come together, reconstruct their relationships and their semantics. And this stage is object reconstruction, music objects reconstruction. And finally, all the retrieved information should be embedded in the appropriate output file, meaning that there should be an encoding stage going on. In the first stage, images of sheet music are subject to techniques such as noise removal, as binarization, deskewing, and the other things that I mentioned. But I will focus more on the other 2 stages, middle stages. Object detection is actually the most research stage for the moment. State of the art today uses deep learning to detect musical symbols in sheet music. Their inputs are diverse, handwritten or typeset, common Western music notation, older, such as menstrual notations. Their main limitations are dealing with the amount of tiny little objects that are very, very dense in sheet music, which is not the case with other computer vision tasks. And that is often dealt by cropping images by state, this way minimizing the image while maximizing the sizes of the objects in there, also minimizing the number of the objects in there. This challenge could have possibly be posed by the lack of a larger annotated data set as well. There is a deep score data set, a new schema data set. The first one is a typeset, very large data set, and the second one is handwritten. Deep scores misses 20% of objects. 20% of the objects are not annotated. Okay. A possible final goal in OMR is end-to-end learning that would not meet intermediate step. Neural networks are already applied to these problems, like text and speech recognition, machine translation. However, these systems are still not adapted to the music nature, let's call it. This work is also limited due to the lack of a better music representation system, as I mentioned earlier. But also, which also poses a problem of not being able to compare current work, missing a standardized evaluation as well. Most of the OMR data sets target different approaches, stages, and objectives within the OMR research. Differences between data sets primarily lie in the annotations that accompany images of sheet music. There are also variations in the type of notation, such as common Western music notation, menstrual notation, as I mentioned earlier, and primary focus, and differences in the printing typeset or handwritten scores. A list of the main data sets is shown in the table that you can see in the slide, so I don't have to go deeper in. The first data set is actually a data set that we're curating at the moment and is ready to be published. So the main challenges of OMR are across different stages, but also OMR as a whole. Low quality of images of sheet music, complex scores, handwritten music, and alternate notations are still challenging for OMR. While most of the work focuses on monophonic scores and leaves aside all the more complex scores that exist and are actually in a higher number, common Western music notation is slightly complex, having dense scores, overlapping symbols, structure complexity, semantic rules that are sometimes violated and sometimes not general enough. For a deep learning approach in particular, we have to be careful while choosing the data sets and while constructing these data sets, as we know that music notation in nature has these huge class imbalance. We have so many note heads, we have so many stop lines, we have so many bars, but at the same time, we're missing the frequency of other objects which appear less is also huge. In this data set we're constructing, we see that only note heads make up 30% of the whole data set. A further open issue is the lack of a large label data set with a broad variety of image quality, and as I mentioned, class imbalance. So future work includes work that we're currently working on, actually, that is publishing and making it open for other researchers, that is the RME dataset, working on evaluation standardization together with finding a better representation system, which would allow deep learning methods to be used as well in OMR. We're also working on object detection and instance segmentation. And finally, the goal is to see if we can tailor musical heuristics and deep learning methods to find to build a better recognition system for optical music recognition. Hope I did not pass the 15 minutes.
No, and because we only have 2 papers this session, there's a little bit of breathing room. Yes, thank you very much for your presentation. That's very interesting. Are there any questions from the audience? Yeah, very interesting. I had some questions coming up that you answered as the talk went on. So yes, I can imagine this is a problem of data sets and labeling. And can you talk a little bit more about the current state of the project after? So this paper was from the 2020?
2019, yeah, end of 2019, yeah.
Right.
So at the moment, as I said, we collected a RME data set that is in collaboration with Steinberg and their Dorico team in London. We were able to dig deeper into the Dorico system and be able to retrieve more semantical information from that. That means we got a lot of musical information on the objects that are appearing. We have the positions for each object. We have the pixelated mask for each object. With these two both, we're working in object detection and seeing how if using other data sets such as MusicEMMA++, which is a handwritten sheet music data set, can we introduce more variations? The data is drawn from a test set that Dorico uses for their own purposes, for their own testing purposes. So the most of the, well, it includes real world scores, but also includes test synthetic graded test scores, which means we have even more variety than a real world score. When it comes to, it could be a problem when it comes to object reconstruction. If we want to also use some heuristics in reconstructing these objects, because some of the relations in there could not musically make sense. At the same time, we're working on predicting the object mask, which is a paper that is, I'm working on to submit to the ISMER conference. So yeah, and we'll have more iterations, and we'll move into the third stage of OMR, that is reconstruction, and seeing if that representation that we got from Dorico is good enough.
Thank you. I see one question here, just in, I guess maybe a general question is, can you talk more about the benefits of the optical approach?
So optical music recognition wants the machine to be able to read music computationally. It would be very not professional to compare it to humans reading music or musicians reading a score, musicians who can read scores, reading a score. So it's called optical because it's using a camera. The benefits are pretty much very huge. For example, most of the musicians nowadays are still writing. Their first piece comes in writing from sheet music. So being able to take, we know that how much problematic it could be and how tiresome it is to transcribe that sheet music to a music notation software. So by using OMR, we can automatically do it by taking a picture of the sheet music. But that doesn't stop there. As I mentioned earlier, if we are able to retrieve all the objects, we could also enable searchability. That would also mean that we could also do plagiarism check in sheet music, since that is not very possible with a graphical sheet. I mean, just an image scanned sheet of music.
I have some follow-up questions also. I'm curious, so as a composer, I've often worked, I enjoy working with paper and pencil, even though I'm also doing a lot of computational work. And I could imagine a system like this could be very interesting for creating, for instance, sequencing a handwritten score or something like this. I'm wondering, well, are there links in the paper already to some usable code that is available for
Well,
trying
there
this out?
are some commercial products which I could list, but they're also, I mean, for example, for object detection, there are some APIs that you can use, web apps that were built from some researchers to just input the sheet music and then be able to see which objects are being detected. But that is not much, in fact, because they're only being detected and nothing more. So the commercial systems are able at some extent to retrieve the music information, but that is mainly a media replayable file in the end, with which you can't really modify or share or, do more with it.
Yes, I mean, I can imagine that maybe in the future it could be interesting also to have access to these extra musical symbols as well, to be able to, for maybe a user of...
Open it in a musical notation software.
I'm sorry, say again?
To just be able to open it in a musical notation software.
Yes, or even, well, to be able to, well, it's interesting from the object segmentation and recognition part of it. Well, personally, I feel like a lot of music notation software is limited in some ways, in that it's very oriented towards historical models of scores, and so, but I see a lot of potential also with this optical music recognition system to be able to apply it towards more contemporary music situations where people could develop systems knowing that it was going to be analyzed and segmented by an AI system, but then also be able to segment out parts that were, for instance, maybe the system knows that some block of graphics are not traditional music notation, but yet are somehow semantic. And so if that can be bracketed as an object, that could be also maybe a secondary level of analysis could be brought in, or something like that.
That would almost be tackled with a system that could tell what genre of music is there, and then well deeper into each piece by its own, let's say, rules or something. Like, contemporary music doesn't have as much rules as historical classical music had, but still it would be interesting to be able to tell a genre by just...
I'm not sure I agree that there are fewer rules, but I think they're maybe less codified, for sure.
Yeah.
There was a hand that was up a second ago, but they've lowered their hand. Are there any other questions? Okay, and there was one, yes, for those who arrived late, there was, the second paper will not be presented today. So just 2 papers in this session. So if there are no other questions, there is a question. Okay, Amir, please. Amir, would you like to ask your question? We don't hear you yet. Okay, unfortunately, Amir's microphone, I guess, is not working. But there is the Slack channel, which is there for more discussion if anyone would like to continue in that space. So thank you again to our presenters and our audience. And I don't have the agenda right in front of me. I believe there's a break now. And does any of the organizers have the agenda at hand? What is the next?
Yeah, we're on our
event?
lunch now, and then we've got the final paper session on time starts at 1:30.
Great. So I wish you all a happy break, and we'll see you at 1:30 Germany Central European time. Okay. Yeah. Thank you, everyone.
Thank you. Brilliant session. Thank you.
Yeah,
Bye-bye.
thank you. Thank you,
Bye.
Rama. Okay, see ya.